And on Wednesday, I mentioned there's a few forms that come up quite a bit. And actually, when you're multiplying them out, you can go through and multiply them out. There's nothing really special about the forms except maybe you're going to save yourself some time. But right after we do this, when we're expanding things, we're going to start learning how to factor. And so factoring is where you want to have a little bag of tricks to save you some time, because factoring can amount to guesswork in some cases, or it's just tedious if you take a systematic approach. So if you look at some of these special forms and learn them the way where we can expand something like this, the a plus b times a minus b, you see we have the difference of squares, recognizing that that's the product of the sum and the difference of those two terms. So this is probably the one that's going to be the most useful for you and the one that should stand out the most quickly. So when you have two terms, ask yourself, are the two terms perfect squares? And so where this comes from, of course, is if we expand it by using FOIL, we'll have these middle terms of negative AB plus AB, and that's why those drop out. And even though we normally get three terms when we're multiplying two binomials, we actually end up with two because essentially the middle term drops out. Another common one is this a plus b squared, where we're going to have a squared plus 2ab plus b squared. One of the very frustrating things for me to see, as students move along, is they'll take a plus b squared and they'll say that equals a squared plus b squared. And that's just not true. You can try it with some numbers, and you'll see that it doesn't work. But it's an easy mistake to make, and it's one of those things that I know you know better, but get used to seeing when you have the sum of two terms and square it, that you actually get these three terms. And if you just say it's a squared plus b squared, you're missing this 2ab, which very often is a very significant term. So here's another one that is perhaps a little bit harder to recognize when we're factoring. We'll talk about that in a little bit. But when we're expanding things, always remember that we can't just simplify by saying a squared plus b squared. It just doesn't work that way. And then if we FOIL that out, that works out to something like this. So you can see where you get two of the those two terms. That 2ab comes from the fact that you get ab twice in multiplying first the outside and then the inside terms of these. You have ab. Now if you make the b either a negative b or you put a negative sign in front of b, you get something very similar, except that only the middle term is negative, because of course when you take the last terms, when you're FOILing this out, that negative b times negative b is going to be a positive b squared. Okay, so here's a form as well that's special. So let's look at some examples and see how these play out in problems that you're a little bit more likely to see. On something like this should, get used to seeing something like this, and it should jump out at you that this is now x squared minus 9. Okay, when you have just a single variable and a constant like this, it's pretty easy. But also you can have a little bit more complicated terms like 2x and 3. And so that first term then squares to 4x squared. So the trick here to remember is that the whole thing gets squared, not just the x. So it's 2x times 2x is 4x squared, and then the last. So if we look at two terms that have two variables in it, we're not going to deal too much with multivariable expressions in this course, but of course we're going to see them now and then, especially with two variables, x and y. So you have the sum and the difference between these two terms, and so that, of course, you just square both of them and you get 4x squared minus 9y squared. Now, when you take x plus 3 squared, it turns out to be x squared plus 6x plus 9. Notice that this 6 is going to be because we have x times 3 times 2, which is that middle thing. And so when we're factoring, and we're going to get to a technique called completing the square, recognizing that middle term is 2 times the product of the terms in the square, that's going to be a pretty important feature to be able to complete the square. So the last term, of course, is going to be 3 squared, but this is 2x, or 2 times x times 3. And of course, if we extend that out, we see that the first and last terms are going to be the first and last terms squared. So the 2x, the whole thing squared, is going to be 4x squared. And then 3 times 3 is 9. So those are the outer ones. But this middle one still follows that rule of taking the product of 2x and 3 and then multiplying it by 2. So 2x times 3 is 6x times 2 is 12x. So there's your middle term. So when you have these special forms, you know, you can multiply it out the long way using FOIL, or you can remember these forms. But like I said, we're going to get into factoring really quickly. So being able to recognize it, to be able to factor these things quickly is where these forms really come in as useful things. Okay, so that's what I said, 2x times 3 times 2. Similar example now with using 2 variables. You look at that middle term, and that's going to be 2x times 3y is 6xy times 2 is 12xy, and there's that middle term. And then the outer terms are just the 2x squared and then the 3y squared. Now, a little bit about the standard order on these things. It probably isn't as big a rule as to make your polynomials go like x to the 5th plus 2x to the 4th plus 3x, and decrease terms there. When we're making individual terms, the monomial terms here, we put the variables in alphabetical order, and then we'll put the overall terms in descending power of the first term. So we have an x squared here, an x, and then no x here. So that's what kind of dictates that order. Now you'll get into more complicated expressions where it's not quite as clear, and the less clear it is, the less it matters. Something like let's say 2x to the 4th y squared plus 3x y cubed. That's probably not as important to put in order because there's more going on there. So really the order is probably most important when you have a single variable. When you have 2 variables, start with the one with the highest power. Okay, so the special forms with a difference between 2 numbers squared. We have the same thing. The outer terms are going to be the outer terms squared, so we have an x squared and a 9. And then the middle term is going to be -2 times x times -3, or not -2. I should say 2 times -3 times x will give us -6x. And then just the similar examples using that form. And you can see how those all come out. You can convince yourself that it's all the same. It's just a matter of keeping everything square. And of course, I made a mistake in my chart here. This should be a plus. Yes?
On this 2x minus 3 squared, was there supposed to be like a square root number there?
There's no square root there. It's just squared. So we have 2x minus 3y. It's going to be the 2x. We're going to square that to get 4x squared. We're going to multiply these 2 things together and get -6xy and multiply by 2, and that's how we get the -xy. And then we're going to have the 3y and square that to get 9y squared. Nathan, does that answer your question?
Wait, where was that mistake you made? Sorry, I just wanted
Well, I had made this a -9. I just didn't
Okay.
complete it. That's all. It's plus 9y squared. And so you can see, I mean, I make that mistake, and it's not because I don't know it, it's just because, you know, I'm in a hurry or just make a small mistake. So it's always good to look things over and correct yourself. Okay, so here's some that I'd like you to try. These should go fairly quickly if you use the special forms, and I'll give you a couple minutes to do these, and then we'll check what you got. All right, any questions on these? All right, so let's look at a couple applications. One of the things that I think I assigned in the tutorial, I don't know if you got to it or whatever, is that you have applications of using these little linear expressions and multiplying them together and getting polynomials that look a little differently. So, you know, we're going to be dealing with a lot of polynomials. It's nice to see some cases where they actually arise. So, when we have a rectangular prism, a box, if you want to think of it that way, some type of not really a cube because the sides aren't all the same. If we have dimensions like this that are stated with a variable, we can come up with a simple expression for the volume. And on this one, your volume, of course, for a rectangular prism is length times width times height. And that should be something that you know. This isn't a great, you know, difficult formula to memorize. This is just one of the handiest geometric things you can remember about volumes. So you take your three terms and you multiply them together, and so here we're going to have an opportunity to use our multiplication rules. Now, so far, I've only had basically two terms that we're multiplying, and when you have more than two terms, like here we have 2n, that's one term, and then we have a 2n plus 2, that binomial is another term, and then we have another binomial term, 2n minus n. The way you do these is just two at a time. You can pick two and multiply them together, and then you multiply it by the third one. And you have two strategies that you can do these relatively quickly. You can go left to right strictly, and then you get you know, 4n squared plus 4n, and then you're going to multiply that by 2n minus 2. But the other thing to recognize is that we have the sum and the difference between two binomial terms. So that one goes really fast, and in fact it collapses down to two terms. So it's actually easier to do it by recognizing the form of this particular expression. And so when we recognize that the sum and the difference here gives us 4n squared minus 4, then multiplying it by 2n is very, very easy. And so we have 8n cubed minus 8n. If you started out from the other direction, the 2n times 2n is 4n squared plus 4n, and then you have a binomial multiplication. You see you'll have a lot more terms, and then you need to collapse them. So sometimes recognizing these special forms saves you a lot of work. And if you do it, then there's also less chance of missing a term or missing a sign or something like that. So you tend to be a little bit more accurate about this. Another kind of problem that you see is areas. You know, we deal with areas a lot, whether you're painting a wall or whether you're buying enough carpet or doing, you know, anything that has to do with the size of things. Areas, especially irregular areas, can be sometimes a little tricky, but if you look at really the situation and ask yourself, okay, what's really going on here, you can make simpler expressions. And in this case, if we want to find the area of the green, what we would do is we would find the area of the green as though it didn't have a hole in it, then subtract the area of the hole. Okay, so this is, we don't have to break it up into anything. We don't even have to know the location of the hole. We just have to know its dimensions. And so we'll multiply the 3x minus 1 times the 2x plus 3, and then we subtract the area of the hole of 2 times 2x minus 1. And so then this becomes a simplification problem. So then we expand out all the terms, and there's no particular pattern here, so we just do it the long way. And then we gather up our terms, and we get a polynomial. Okay, so these aren't the most exciting examples, but you'll see them. Part of the questions that you'll get in dealing with polynomials applications will be constructing a few. And so there's nothing special about it. It just, as if we had 3x minus 1, instead of that if we had a 10, and instead of the 2x plus 3 if we had an 8, you could calculate that area fairly easily. Treat your polynomials as though they were values, and make sure you're using parentheses properly, and then you'll get to where you need to go without much difficulty. Yes?
What's the little 2 inside the white box?
That's the height of that.
Oh.
So this is going to be essentially 2 wide and 2x minus 1 long. And so when I'm calculating the area there, I'm going to subtract the area of 2 times 2x minus 1. Okay, so you know how to add polynomials, you know how to subtract polynomials, and you know how to multiply polynomials. Polynomial division we're going to do a little bit later, because one of the tools that's helpful when you're doing polynomial division is factoring. So we're going to look at factoring first and go through all the cases of factoring, and then we're going to return to polynomial division. So you'll have the 4 basic operations under your belt when we're dealing with polynomials. Okay, so first we're going to kind of do this in the reverse order that we did multiplying polynomials, because there is a certain kind of reciprocity or symmetry in factoring and multiplying things out. So we're going to take it perhaps in the reverse order of what you may have seen it in high school. Okay, so when we have a polynomial and we multiply it, we get an expansion. We can factor it if we start with x squared plus 3x plus 2. When we say we want to factor it, we want to come up with 2 factors or more that give an equivalent expression. Now there's a lot of reasons why we would want to do this. First off, if we have an equation with a polynomial, we're going to find that solving the equation when it's a series of, or a sequence of factors, is going to be easier than if we try and solve it directly when it's the sum of different terms. And so that's going to be the upcoming topic from this. The other thing that it helps us do is that if we have the ratio of two polynomials, we can't directly cancel factors or terms individually, but we can cancel factors. And just like if we have 3 plus 2 over 2, you can't really just cancel out the 2's, right? You need to first add the 3 and the 2, and you get 5, and you have 5 halves. Same thing with polynomials. We can't just pick and choose individual terms in a polynomial, but if we factor it, then we can cancel out entire factors. And so factoring is very useful in simplifying these ratios of expressions. And of course, I already mentioned we'll be able to solve some polynomial equations by factoring. So let's look at factoring by grouping and some special forms, and then next we'll do the factoring that you probably always think of when you think of factoring as factoring trinomials. That's probably the thing that's emphasized the most in high schools. I want to spend some time on factoring by grouping, because you'll be able to factor more complicated expressions, more complicated polynomials, if you learn how to factor by grouping. And I know there's a lot of techniques out there that work, that are solid in terms of factoring, but sometimes you tend to miss how to factor by grouping, because these other ones are used in the simplest cases, and so you forget about the factoring with grouping. So I do want to address that one first. Okay, so the first thing that we do when we factor is that we always want to factor out a common monomial factor. Okay, so we don't necessarily want to factor out a binomial or a trinomial first. We always want to look to see, is there something we can factor? So let's say we have an expression, a polynomial that has a 9x to the fourth, and a 6x cubed. If we look at those factors, okay, the coefficients, we factor those and we get, 3 times 3 for 9, and then 6 is 2 times 3, and we see that we have 3 in common. And so the factor that we can factor out if both of these are in common is, of course, the x cubed, because x to the fourth is x cubed times x. And then we can also factor out a 3. So when we have something like this, where we have 9x to the fourth plus 6x cubed, the first thing to look for here, and this can be 2 to however many terms end up in an expression, is always look for the common monomial factor. This is the easiest thing to overlook, and it's probably the simplest thing, or the simplest way to get it down to a reduced problem, which essentially makes things easier. Yes.
So why was x cubed a common factor? Sorry, I just missed what you said.
Why is the x cubed in common?
Common,
Yeah, because x fourth is x times x times x times x. X cubed is just x times x times x. So they have the 3 factors of x in common. So when you're looking at this one, the first thing to ask is, can I take out a common monomial factor? And indeed you can. And then you end up with something that, can you factor 3x plus 2? And the answer is no. If you're looking for other techniques in factoring, you're going to be scratching your head for a long time. The easiest first step to make in factoring is that common monomial. Yes?
So I understand that you got 3x cubed. How did you get 3x plus 2?
Because I'm factoring these things now. Let's say we have 9x to the fourth, and I know my common factor, the ones that I can take out of both terms, is this. So what times this gives me that? Okay, so that's going to be 3 times 3 is 9, and then x times x cubed is 9 to the fourth, so that's going to be that first term. Same thing with 6x cubed. If we have 3x squared, the first thing, well, when we look at the coefficients, it's going to be 2 times 3 is 6, and then actually this is 3x cubed. And then we can factor out the x cubed, so we just end up with a 2. So when we factor this whole expression, we get the 3x plus 2. Okay, so look at it backwards now. If I were to distribute this, I'd get 3x times x cubed equals 9x to the fourth plus 6x cubed. So we're thinking, how do I go backwards from that?
So you're just putting the leftovers in the parentheses.
Yeah, you can look at it that way. It's not really left over, though. It's still part of the expression.
Yeah, but like you factored out and then the numbers that are still there.
Right. So you can look at it as these are the common terms, and these are the unique terms. And then the product of the two gives you the term that you started with. Okay, so let's look at one like this, where we have 28x squared plus 16x minus 8. Now, if you're used to factoring trinomials, you'll start your bag of tricks on this thing directly. But what I'm suggesting is that you first look, are there any common monomial factors? First thing to always look for, is there an even number that you can factor out? And you can certainly do that. If you look at 28, that's going to be, what, 2 times 2 times 7. 16 is 2 times 2 times 2 times 2. Okay, and then 8 is 2 times 2 times 2. So it looks like we have at least 4 that we can take out, right? Everyone shares the 2, so if we factor out a 4, we get 7x squared plus 4x minus 2. Now this is a lot easier to think about in terms of factoring further than this one. And so if we have something like this, we think, wow, x to the fourth, x cubed, x squared, that's really going to look pretty ugly when we factor that. It doesn't really look like, a quadratic expression. But if we look at the individual factors here again, 2 times 2 times 5, 2 times 2 times 3, and 2 times 3 times 3. So what's in common?
squared.
4x squared. Yeah, we're looking then, that's from the coefficients is 4, and then, not 4, because 18 is not divisible by 4. It would only be 2, right? Okay, and then we have an x squared that is common in all of these, so we'll take out the 2x squared, and we end up with 10x squared plus 6x plus 9. Now that looks like something we can handle with as a trinomial. Okay, so here's one for you. Oh, wait a minute, no. I want to make a comment about -1. One of the most helpful ways to get this into a more recognizable fashion is whenever your leading term is negative, at least factor out a -1. Okay? So when you do that, this thing turns around into something that looks a little bit nicer. Like it is possible to factor, or is it possible to factor this? Well, that's a little harder question than asking yourself x squared minus 3x plus 1, because all the techniques that you usually talk about with factoring rely on the first or the coefficient of the leading term being positive. So whenever you see the negative, first factor out, and then make sure you factor out the rest of them so all of these signs change. Okay, so a plus goes to a minus goes to a plus, and so we end up with this thing properly factored. Another example. So we can factor out a -4 here, and we get x squared plus 5x minus 3. Okay, so yeah, just to emphasize the point, make that leading coefficient positive. That will greatly simplify your task. Okay, so here's some for you to try now. I'd like you to factor out just the common monomial factor. Don't worry about the rest, okay? So that's including a -1 if it's there. So what would we get here? We're going to do a few of these in succession here. Actually, I think I have all of them listed first, so we can do a group of them. Yeah, let's do a group of them here. Okay, so good. Any questions on that? Okay, so let's directly get into factoring by grouping now. Now, if we have some factor that is that we're multiplying by two different terms like this, and I'm making a squiggle just so you don't really worry about what's inside there, except that it's the same. When you have these two groups, you can still factor out that entire group and get whatever that group is times 3x minus 2. And so hopefully this visually is a little easier to see, because you can imagine this just being a number or a letter or something. If this was an A here and an A there, you can factor out the A and you get 3x minus 2. But it can also be an expression. It can also be a binomial expression or a trinomial as well. And so when we have something like this, okay, perhaps that's a little bit more difficult to see how that factors, but look at what's in common. The 2x plus 1 is in both terms here, so that factors out. And so we get the product of two binomials by factoring this. And so recognizing this pattern and being comfortable with the fact that you can either factor it by putting it on the left or on the right, it doesn't really matter, but you know, that 3x and that -2 form a binomial, and then that 2x plus 1 just nice cleanly factors out. So look at this one and then see if you can see what that factors out to be. Yes?
For the first, your example, how come the 2x plus 1 isn't squared?
How come the 2x plus 1 is what?
Isn't squared.
It's not squared because it's the same factor. It would be exactly like doing this, where when we have 3a minus 2a, we can factor out the a and get 3 minus 2. We don't square it. And so if instead of a we have 2x plus 1, we're doing exactly the same thing. We're taking out this single entity and factoring it out. Okay? So it's just like if this were a single variable or a single number. Okay, so who got this one? Stella, did you get it?
5x squared minus 2, parentheses, round those ones, and then 6x minus 5.
Yeah, good. And it doesn't matter what order you put it in. Remember, multiplication is commutative, so if you put the first group second, that's not a big deal. Okay, here's another one. This one, though, think about what's implied here when you're doing this. Is the sun on the screen bothering? Should I? Okay, who got that? Yes.
All right, parentheses, 2x plus 3, parentheses, 3x plus 1.
Plus 1. Okay, so remember that whenever you have these groups, you have this implied coefficient here. Okay, so that's that 1 is going to be very useful. And so, strictly speaking, when this is written out, it's possible to have this thing written with parentheses and having this as just plus 2x plus 3 without parentheses. You're perfectly justified into making groups that you can factor out. In fact, when we use this to factor trinomials, you'll be making a group to factor out. All right, so then a little variation on that theme. Abby, you put that pencil down definitively. You know it, right?
It's 4x plus 2 parentheses 7x minus 1.
Okay, great. Okay, everybody seeing these okay? All right. So let's start applying this, factoring by grouping. So the first application is when we have something that looks perhaps not factorable or easily factorable. We have an x cubed, x squared, an x, and a constant term in there. So how do we factor this? One of the key things to look for is to look for pairs. And here we have a coefficient of 1, and then the x has a coefficient of 2. So immediately think in your brain, okay, we'll multiply that by 2. Take a look at the second coefficient. We see a negative 5. And here we see the constant term is 10. So perhaps what we can do is make a grouping here by doing something like this, where we say, okay, let's factor out the x squared and factor out the 2. And then we factor it a little more by taking out the x minus 5. Now it takes a little bit of looking to see, the little clues, like, you see the potentially a 2 being factored out, or potentially an x squared being factored out from the first 2, and a 2 being factored out. One of the things about factoring is that when you factor it when you completely factor something, that factorization is unique. So, like, there's several ways to factor something like, let's say, 20. You can say 20 is factored by 4 times 5, or it's 2 times 2 times 5. Well, 4 times 5 isn't fully factored. So if you factor the 4, you get 2 times 2 times 5. And so any number that we factor, if we factor it all the way down to prime numbers, it'll be unique. There's only one set of numbers. You may get them in a different order depending on the method that you use, but ultimately they'll all be there the same. Polynomials are the same way. When we factor it to the point where we can't factor anymore, we're going to have a unique factorization that'll come out like this. And so noticing these little patterns that you can factor, let's say this thing, if we tried to factor out the 2 on this one, and instead of x minus 5 we get x minus 4, we couldn't factor out that group because x minus 5 and x minus 4 aren't the same. So you're done at that point. There's no more factoring to be done. But since we have this common factor of x minus 5, we can still factor. So no matter how you factored this thing, no matter what technique you'll use, you'll be done when you get to this answer. Okay, so factoring by grouping, sometimes you can take a different route by which ones you pair up, but certainly you'll get to the same place. Okay, and one of the ways that you can help yourself here is to always start out by putting something in standard form where you have the declining degrees like this, because those first 2 then you're almost always guaranteed to be able to factor out x squared here, and then you're left over with just factoring out a constant term on the second one. Okay, so let's look at a different one here. Notice here that I'm not, that this isn't fully simplified, right? This is x squared plus 25x plus x plus 25. If we simplify this, we get x squared plus 26x plus 25. But I'm doing this deliberately because when I have this combination, I like the fact that I have that 25 in every other term. So when I factor by grouping, I can factor out an x on that first 2 terms, and that second one doesn't factor. I just group it as x plus 25, and all of a sudden now I can factor this to x plus 25 times x plus 1. So I haven't told you how to get to this point yet, but hopefully you can see that there is some advantage to writing this thing in not simplified form because it factors by grouping. So here we'll take another one that I've written in a similar fashion where I've taken this linear term and I could simplify that down to negative 4x, but I'm choosing to keep it like this because I notice that if I take out my x here, I get x minus 6, and if I factor out a 2 here, I get x minus 6. So I get these 2 groups, and then that x minus 6 can factor out and I get x plus 2. So there's other ways. If you start with x squared minus 4x minus 12, there's other ways to factor that. But here's one that if somehow magically I have the insight to say negative 6x plus 2x, I'll be able to factor it. Okay, so I'm kind of going backwards on doing this. We've learned how to ultimately factor by grouping. Now I'm showing you that there may be a trick to factoring ones if we know how to split this up. And so that's the next thing I want to get to. But first, here's a couple for you to try. So what do you think? Anybody get this one? So we're going to factor in pairs. Remember, we're looking at the first 2 terms and the second 2 terms. Factor them by taking out the common factor and see what you get. Okay, Stella, did you get it?
I got the first 2 terms, the common was x squared. So x squared, then parentheses x plus 2. And then the next set was 2 was the common, and parentheses x plus 2.
X plus 2, great.
X squared plus 2 and x plus 2.
Right, so that was the first step, and then you got the second step of factoring out the x squared plus 2. Okay, everybody get that? Okay, so now we'll try one that has that, well, some negative numbers in here. So let's look at this one. Morgan, did you get it? This one, Morgan, I'm sorry, I should be more specific.
3a squared minus 2 and a minus 4.
Tell me again?
3a squared minus 2 and a minus 4.
Okay. Like that. So you said the first pair, the second pair is negative 2 times a minus 4, and then you can factor out the 3a squared minus 2, right? Is that where you arrived? Okay, good. All right, so let's move on here. And actually, I think at this point, I want to stop. We're going to return here on Monday, and I think this is probably a good enough chunk. And you'll have some homework on doing this factoring.